I'd like to give you a quick introduction to the concept of entropy. Now, entropy is simply a tendency to disorder. So let's take a look at an example of that. All right, let's say you have a room here and you're a clean freak. If you're a clean freak, then there's a place for everything and everything's in its place. And there's only one possibility that allows a room to be clean, and that might be this one, for example. However, there are almost infinite possibilities for making that room not clean. All it takes is just for one of these items to be out of place and it would be considered not clean. And this is just one possible scenario, which would be for not clean. This could be over here, these could be arranged differently here, these pillows could be down on the floor, this could be over on its side. There's infinite, almost infinite ways that this can be arranged and would be considered not clean. So all we're saying here is entropy is just the tendency for the greater probability arrangements to occur and not just to be stuck in just a few possible arrangements. There's also relevance to chemicals, and these are the rules that we talk about for entropy. The first thing is the entropy of anything that's not at 0 Kelvin will be greater than 0. At 0 Kelvin, all molecular motion stops. That's when the entropy would be 0. So if we're talking about temperature above 0 Kelvin, then we're talking about a positive entropy. Let's take a look at some of these in the table, and you can see that the vast majority of the values are indeed positive. That's what we'd expect. The only ones that are not positive are the ions, and that's because ions are treated differently to regular compounds. The relative entropies of ions are different to solids, liquids, and gases. And if you want more details about that, I'll talk about that in class. Just realize that as far as everything else goes, aside from the ions, you're going to see positive values. Alright, what else? Entropy of gas is greater than ions in solution, is greater than liquid, is greater than solid. Alright, let me show you something that illustrates that. In a gaseous state, you can see molecules are flying everywhere, and there's lots of different ways that a gas can be arranged, so we're talking about lots of arrangements, which means high entropy. An ion in solution, you've got lots of ways these ions can be arranged, and you've got all the solvent molecules in here as well, so there's lots of different kinds of arrangements that can be made for ions. Liquids, we're talking about pure liquids here, liquids without anything dissolved in them. Won't be quite as much as ions, but there's still going to be a fair amount of disorder going on with these molecules moving around each other. Not quite as much as in a gas, because a gas is going to have the molecules not touching. The liquid has to have the molecules touching. Then you've got the solid, a very highly ordered state where the molecules can't do very much except pretty much sit where they're at. So in summary, we can say the entropy of a gas is going to be greater than entropy of ions in solution, greater than liquids, greater than solids. The other thing we notice is that bigger molecules have more entropy than smaller molecules of similar composition. And an example of that might be something like S8 solid is going to have greater entropy than just S solid. So single atoms of S arranged like this, it's going to have less entropy than S8 molecules, because S8 molecules can be arranged in different ways. We can have and still be joined together, so it'd be 1, 2, 3, 4, 5, 6, 7, 8. And that chain of S's can have lots of different combinations. So bigger molecules tend to have more entropy than smaller molecules. Going back to here, the measurement of entropy or change in entropy in a chemical process is going to be the entropy of the products minus the entropy of the reactants. You'll notice it's always products minus reactants, just like it was for enthalpies and heats of formation. So let's look at two examples of those. So here's a situation where we've got N2O4 gas and it's turning into N2 gas plus 2O2 gas. What I want you to see here is there's going to be more entropy on the product side than the reactant side because we've got more gas molecules floating around. We've got more opportunities for disorder, many more possible combinations. This can be here, this can be here, this can be here, this can be here. Whereas this one can just be in sort of different locations. It won't have as much entropy as what we've got going on over here. Alright, so what that means is if we were to measure the delta S, it's always products minus reactants. We'll have a big value minus a small value, so the delta S will be positive. So when there's more entropy on the product side than the reactant side, the delta S will be positive. That's a very important point. Here is another example. We've got Pb2 plus 2Cl minus, so we've got aqueous ions in solution on this side, and over here we've got them going to a solid. Now, if the PbCl2 is in a solid, it's not very ordered, but the ions in solution have lots of different combinations, lots of different ways they can be arranged. So again, it's products minus reactants. We're going to have a small value minus a bigger value, so the delta S value will be negative. So the main point here, if there's more entropy on the reactant side, then we're going to get a negative delta S value.